Good afternoon to everyone. I'm grateful to the organizers for this opportunity. This work I have done in collaboration with Professor Sibasis and Dr. Yuki. We use the refrigerator from home to space and lab to industry. What refrigerator does is, it absorbs the heat from the cold bath and we supply the input work so that it absorbs from the heat from the cold bath and transport to the hot reservoir. The quality of the refrigerator is given by the two parameters, namely the cooling power and the coefficient of performance. When the refrigerator works reversibly, we get the maximum coefficient of performance with a zero cooling power. The disadvantage of the Carnot, the maximum coefficient is given by the Carnot value. And the disadvantage of the Carnot refrigerator is that it works reversibly, which takes the infinite amount of time, so that we cannot cool the system in a finite amount of time. And also, the hot and cold reservoirs has the infinite heat capacities. So even though we take any finite amount from the cold reservoir, its temperature won't drop. In real situation, for example, if you want to cool this Ramanujan hall, then it has a finite number of molecules, so that it has a finite heat capacity. And the environment, which is very, very large compared to the hall, therefore we consider as the hot reservoir which has with the infinite heat capacity. So when we absorb the heat from the hall, then its temperature drops. So we want to cool the system some temperature from Ti to Tf, which is the lower temperature. What is our goal is to minimize the input work for the required cooling, so that we can save the cost. To perform our study, we consider the steady state refrigerator instead of the usual cyclic refrigerator, which is a Carnot refrigerator. The input work is given by the input power is given by the F into x dot. The x dot is the piston velocity. This input power we can also calculate using the first law of thermodynamics. Then we calculate the entropy production rate at the reservoirs. Next, what we do is that the time derivative quantity and its coefficient we separate together. The time derivative quantity we call it as a thermodynamic flux, and then its coefficient we call it as a thermodynamic force. What we mean by thermodynamic force is that which is the one which drives the thermodynamic process, and response to the thermodynamic force is we call it as a thermodynamic flux. In general, when this heat transport process as well as the piston movement happen simultaneously, one can influence another. Therefore, both the flux have the function of x1 and x2. So when the temperature difference between the hot and cold reservoir is very, very small, we can write J1 and J2 as a linear function of x1 and x2 using the Taylor expansion. Here Q square is a coupling constant. In real situation, when we transport the heat from the cold bath to hot bath, we don't have the perfect insulator. Therefore, heat leakage is unavoidable. Here by hand, we will add this heat leakage term gamma C J1 square. The physical reason behind we add this is, for example, the friction force, which is the function of velocity. Similarly, the heat leakage term also should be a function of x1 and x2. If you go to the higher order, then the problem becomes difficult. If you go to the lower order, then it's become just altering the Onsager coefficient. Therefore, this is the simplest model where we can include the heat leakage term and then solve analytically. Here, the absorbed power is given by this, and then heat rejected to the hot reservoir is given by this equation. So the entropy production during the process should be greater than or equal to 0. This gives some constraint to the Onsager coefficient. In our study, we also use that Onsager reciprocity relation, which means that near equilibrium condition, the microscopic dynamics of the system also follows the time reversal symmetry. We consider that the cold bath has a finite heat capacity CV, and we assume that during the heat transfer process, the cold bath does not change its volume. Therefore, the absorbed heat flux is given by minus CVT dot. With that, now the total input work can be calculated using equation 9. Here, the total heat absorbed from the cold bath is nothing but change in its internal energy. And in order to minimize this input work, we use the Euler-Lagrangian method. So this is the J3 for our system. Look, it is difficult to solve Euler-Lagrangian equation for this heat flux. Therefore, we consider a simple situation where T dot is very, very small compared to 1. So that J3 becomes very simple. So we can solve this answer Euler-Lagrangian equation. So this is the optimal temperature rate we get. For this optimal temperature rate, we can calculate the input work as well as the input power. Here E is the exergy. Actually, it is definite for the heat engine. Here, with the little bit abuse of the terminology, this is what we get the exergy. What it means is, we want to cool the system from initial temperature to final temperature. When the refrigerator works reversibly, then this is the minimum work required to cool the system. That's what we call it as exergy. Here we can see that we cannot further, this input power monotonically decreases with the tau. Here the tau is a time duration which cool the, where the refrigerator cools the system from initial temperature to the final temperature. So therefore, we calculate the coefficient of performance as a function of input power and exergy, and this epsilon max is the maximum coefficient of performance when the cold bath has a finite heat capacity. So therefore, it works reversibly. And in this plot, we plotted coefficient of performance as an input power. When the input power increases, the coefficient of performance drops because when we increase the power, it decreases the process time. Therefore, then the irreversibility decreases, which leads to decrease of the coefficient of performance. Here, when we increase the exergy, the coefficient of performance increases. So, we studied the coefficient of performance of the nonlinear refrigerator in analytically feasible case, and we find the optimal temperature rate for the cold bath, and we found that the coefficient of performance decreases nonlinearly with the input power. Thank you for your.
Thank you so much. Any questions?
No, I just wanted to ask this. There is this calculation which was done long time back regarding engines, no?
Yes.
The maximum power, efficiency at maximum power.
Yes.
Right?
Yes.
So I would have thought that something similar would be here, no? Like if you wanted to calculate, let's say, the quality factor.
Yes. Yes.
So why doesn't that argument still apply?
Yeah, it is not always obvious the optimization procedure which works for heat engine. We cannot do it for.
So that optimization procedure doesn't work here
Doesn't
in this
work.
case?
Yeah.
And why is that? Do we understand it?
The reason is that it is not clear. It's always that the power, what we want to maximize for heat engine is that efficiency and power. That's always clear. But when we go for a refrigerator, then we look for maximizing the coefficient of performance and the cooling power. It's a model dependent. So which parameters which suits for optimization, it depends on the model specific. For example, in this case, in the case of heat engine, we can once again maximize the power. But in the case of refrigerator, it does not have the minimum. Yes, it's monotonically decreasing. It does not have it.
If there are no more questions, let's thank the speaker.